Akhirah, again, I never know how to start these videos. But yeah, Unit 4, gas laws. Yay, let's do this. Okay, so there's three different phases. Obviously, this is, I feel like everyone knows this, but there's solid, liquid, and gas. So what are the differences between these three phases? Okay, so shape and volume wise. In a solid, you have a definite shape and volume. In a liquid, you have a definite volume, but you don't have a definite shape. The liquid changes depending on the container it's within. And then with gas, both the volume and shape change. Yeah. So how far apart are the molecules, right? In a solid, the molecules are very, very close to each other. They're very tightly packed. In a liquid, they're close, but not as close as a solid, which allows them to change shape, right? But doesn't allow them to change volume. And then with the gas, they're very far apart. They can go wherever they want, which is why, they have a changing shape. Volume, they're very far apart, right? And then intermolecular attraction, pretty much how much are the molecules attracted to each other, right? Solids have a very high intermolecular force, intermolecular attraction, because they're so close together. Liquids have a medium, and gases have low, right? And the kinetic energy, so pretty much kinetic energy is kind of like pretty much temperature, right? So solids, they're very low kinetic energy. They're like not low temperature, but like they don't move a lot. They don't have that much kinetic energy. Liquid, they have a medium kinetic energy, and then gas, they have the highest kinetic energy. Or I guess it was plasma, but like that's not important. Anyways, okay, so English is hard. Kinetic molecular theory, right? So this theory explains how gas particles would behave in an ideal environment. So what are the like 5 parts, I guess, of this theory? Number 1 is that a gas is composed of individual particles, which are always going into a straight line of motion. They're always moving straight. Me. Anyways, number 2, so not all gas particles have the same kinetic energy, but if you take the average of all the gas particles, the average kinetic energy of all the gas particles, it should equal to the temperature of the gas as a whole. Right? 3 is that collisions between particles are always elastic. Energy is never lost. You have the same amount of energy before the collision and after the collision. It's just that the energy gets transferred between the particles. Number 4 is that there is no attraction between said gas particles, and then the volume of one gas particle isn't important. Doesn't exist. Just pretending it doesn't exist. Yeah, right. So kinetic molecular theory: temperature is the average kinetic energy of something. The temperature is the measure of how fast said molecules are moving, and then the average kinetic energy of gas molecules and temperature have a direct relationship. So the more kinetic energy a gas molecule has, the higher the temperature. If you were to graph it, it would have a positive slope. I don't know why I think of everything with graphs and math. It's really, I don't know. That's how my brain works. Okay, so temperature kinetic energy relationship, as mentioned in the previous slide, they have a direct relationship. So an increase in kinetic energy will mean an increase in temperature and an increase in molecular speed. That's what kinetic energy is. Anyways, so ideal gases, right? So these ideal gases follow these rules of kinetic molecular theory, right? And the best condition for ideal gases is to have high temperature and low pressure, right? And the way I remember high temp, what was I saying? I don't even remember what I was saying. What? Never. If I don't remember, it's not important. Anyways, the thing is, real gases are not ideal. We do not live in a perfect world, sadly. Trust me, I wish I did, because then, I wouldn't be doing this right now. Actually, would I? I probably would, but then whatever. But real gases, they have volume, they do attract each other, right? And they are sometimes in conditions that are not ideal. Sometimes they're in low temperatures and they still have high pressure. So screw them. Everything will be perfect. I don't know why I said it like that. Anyways, Boyle's law. Okay, so pretty much, Boyle's law talks about the relationship between pressure and volume in a closed system, where temperature does not change. It remains constant, and pressure and volume. Boyle's law shows that they are inverse. So if like pressure were to increase, then the volume would decrease, and if the pressure were to decrease, then the volume would increase, right? And then the equation for Boyle's law is initial pressure multiplied by initial volume is equal to final pressure multiplied by final volume. So yeah, and then if you like, and then you kind of just plug in the numbers and you solve for whatever the missing thing is, because math. But yeah, pretty much in Boyle's law, pressure and volume um they have an inverse relationship. When one goes up, the other goes down. Okay, Charles' law, right? So Charles' law talks about the relationship between temperature and volume when pressure is constant, and the Charles' law says that the relationship between temperature and volume in a closed system is direct. So if one goes up, the other will go up. If one goes down, the other will go down, right? And then the equation is initial volume over initial temperature is equal to final volume over final temperature. And then you just do the same thing as the previous one, plug in numbers. Like let's say you have to find for the final temperature, plug in whatever numbers they give you, and you get it. Lucas's law, right? So this his law talks about the relationship between temperature and pressure if volume remains constant. Okay, and he says that the relationship between temperature and pressure is direct. Okay, one goes up, the other goes up. One goes up, the other goes up. One goes down, the other goes down. Okay. So the equation for pressure and temperature is initial pressure over initial temperature is equal to final pressure over final temp. And then these will be, if you were to put these in a calculator, in one of those graphing calculators, and then, whatever, see the graph, is what they would look like. Pressure and temp, you can see they have a direct relationship. Pressure and volume, they have an indirect relationship. Well, it's not technically whatever, it goes down, right, whatever, right? And then volume and temp, they have a direct relationship. Right, and then the combined gas law, right? So there will be times where all three variables will change within a problem. That's when you use the combined gas law, and it's actually on your reference table. I don't know where it's on the reference table. Let me check actually, since I have it right here. Yeah, so the combined gas law equation is on table T for reagents chemistry. Okay. And then STP, standard temperature and pressure. So if they don't give you, a lot of times a problem would be like, oh yeah, this gas is at STP. So what does that mean, right? Pretty much table A, front page, read the first table. It gives you the standard pressure, and the standard temperature is 273 Kelvin or 0 degrees Celsius, and then for pressure it's 1 atmosphere or 101.3 kilopascals or 760 torr, or what's the other one, like whatever. I don't even know I forgot what that stands for. Anyways, we're gonna pretend I know what that stands for. It's been a while. It's been a couple of months. A lot of months. I don't know I forgot what that means. But yeah, unless the question says otherwise, you just assume, oh, it's at STB. Yeah. So these are some examples of this is an example in Boyle's law, right? So which talks about the relationship between pressure and volume, right? So if 80 milliliters of gas is stored at a pressure of 101.3 kilopascals, wow, I really can't do numbers today. What will be the new volume if the pressure is increased to 106.3 kilopascals where the temper remains constant? So, I guess, right? I feel like, you know what? Figure that out. If you can't do it, I'll do it anyways in a few minutes. So. Okay, so, how you do this? So, you make a list. I mean, I don't do this, but, I mean, oh crap, I just realized you can't hear me because my, you need to remember, I have to put my mic near my mouth for it to register my voice. So how do you start this problem? You make a list. I mean, I personally don't, but, you know, it helps people, so you can make a list. Okay, so the list. What's the initial pressure? The initial pressure is 101.3 kilopascals. What's the initial volume? 80 milliliters. Then we need to find the new volume, so let's use, I guess, x as a variable, and then final pressure is 106.3. So, I just realized, okay, well, that's not very useful. Okay, well, that's fine. So, Boyle's law, the formula for Boyle's law is PV equals PV. Yeah. Or if you can't remember all those separate gas laws, you can just use the combined gas law and then just kind of get rid of the variable that doesn't change. So like temperature doesn't change, so you can use the combined gas law and just pretend that temperature doesn't exist. So, you know, you plug it in, so it would be 80 multiplied by 101.3 is equal to 106.3x, right? So if I do the math real quick, 76, yeah, round to 76. I mean, there's a bunch of decimal places off from my point, right? So that means the new volume would be 76 when rounded to the nearest whole number. Would you round to the nearest whole number, or would you round it to one? You might. Pretty sure you round to one decimal place. I forgot how significant figures work. Those are important, so. But I forgot it. Whatever. Okay. Ooh, another one. Okay. A sample of gas has a volume of 16 liters at a pressure of 3 atmosphere. What is the pressure if the volume is decreased to 6 liters at a constant temp? So I'll let y'all do this one too. I'm back. Okay, so you make the list again. What's the initial pressure? 3 atmospheres. The initial volume is 16. And then we are figuring the new pressure out, which would be X. And then, and then the new volume is 6. So the equation will be 16 multiplied by 3 is equal to 6x. So it would be that means the new pressure will be 8 atmospheres. Look at me doing mental math. I'm just amazing. You know, you know what? Maybe I should go into Harvard. I'm kidding. I'm not that smart. Whatever. Anyways, Charles' law. Okay, relationship between temperature and volume. Oh, okay. Number 1, what will be the new volume of 50 milliliters of a gas that is raised from 27 degrees Celsius to 127 degrees Celsius at a constant pressure? Okay. You have fun. Okay. Okay, I'm back. God, this headphone really hurts my ear. Oof. That reminds me, I need to get my ear checked. I'm pretty sure I fucked up my hearing, but oh well. Okay, so list time. Initial temperature 27. And then initial volume 50 milliliters, right? A new temp 107, and then we need to find out the new volume, which is X, right? So use the what's the equation? The equation is volume over temperature, right? So I need paper for this. I can't do this in my head. I'm not that smart. I wish I was that smart. I would that would make life so much easier. So it would be 50 over 27 is equal to finding the new volume. So X over 127. And then if I do some math, 235. So, yep, that's the answer. Look at me doing math. They say gays can't do math. Yeah, we can. I need to stop. What is it with me spilling drinks on me? Honestly, I need to get better hand control. Whatever. Number 2. A sample of gas has a volume of 150 milliliters when its temperature is 17 degrees Celsius. If its temp is increased to 32 degrees Celsius, find the new volume assuming pressure remains constant. So you guys have fun with that. Okay, I'm back. So, this time again. Initial temp, 17 degrees Celsius. And then initial volume, 150 milliliters, right? And then the new temp is 32 degrees Celsius, and then you gotta find the new pressure, right? So, you plug it into the equation, right? To get 282 milliliters as the new volume. Round to nearest whole number, because I don't like dealing with decimal places. Okay. Okay, and now this is combined gas law example. So if, all the variables were to change, how would you do this? Okay? So, a sample of gas has a volume of 500 liters when its temperature is at 25 degrees Celsius and its pressure is at 39.9 kilo. Honestly, you couldn't have just rounded that to 40, or whatever. And its pressure is 39.9 kilopascals. What volume will the gas occupy at STP? So, you have fun there. Maybe. I don't know. Okay, so this one was a bit of a doozy. Made me want to cry inside a little bit, not gonna lie. Not even gonna lie. Okay, so let's do this. Okay, so, okay. Where do I start? I'm trying to think. Where shall I start? You know what? Let's just start with the list. Initial pressure is 39.9. Initial volume is 500. And the initial temp is 25. Okay. And then the gas will occupy at STP. That's what I want to know. So what's STP? STP is 101.3 kilopascals, but it's 0 degrees Celsius. And if you know anything about math, you can't divide by 0, because 0 likes breaking math. So, what do you do in this situation? What you do in this situation is that you convert the Celsius to Kelvin, right? Now how do you do that? Well, it's on table 2. You take the Celsius temperature and you add 273 to it, right? So that means the initial temperature, 25 degrees Celsius, will become 298 Kelvin, right? And then the 0 degrees Celsius will become 273 Kelvin, right? But then it's just the same. You plug into the equation, poof, and then if I did this correctly, you should get 180. I'm gonna actually double check my math real quick because that was a bit of a doozy, and I kind of don't trust myself, Loki. That's right. That's right. And then 544 6350 divided by 30 hard shot punchar. Yeah, I did right. 180. Okay, so I am pretty sure that's it. Oh, that's it. So, that's gas laws. Um, just honestly, just a lot of math. Yeah, that's what I remember from gas laws. Well, yeah, I don't. I also never know how to end these videos. I never know how to start them. I never know how to end them. Always the most awkward parts, in my opinion. But I hope you have a good day.